Okay, so hi to everyone online. Um, my name is Dan Levy, and I am a researcher in General Motors Center in Israel. I will talk about training models for road scene understanding with automated ground truth and show results from multiple studies that have been done by all the group members here shown in this slide. Um, And please don't hesitate to interrupt me if you have questions throughout the talk. Um, so just a few words about my wait a minute. Oh, about the place I work in. So the GM Advanced Technical Center in Israel is both an engineering and research site of General Motors in Israel, with several hundred employees, and we are mainly focused on automated driving technologies, but also other future technologies in the vehicle. And what I will talk about today, I will first introduce something that probably most of you know is what does it mean to do road scene understanding for autonomous driving. And then the main topic of the talk will be on acquiring training data with automated ground truth as a general approach. And after I review the general approach, I will show several test cases which we tried and have results with. And these include general obstacle detection, road segmentation, general obstacle classification, curb detection, free space detection, also car pose estimation, and others. And I will discuss the challenges and the limitations of our approach. Okay, so first, what is onboard road scene understanding? So basically, an autonomous vehicle has to detect all the relevant objects in its surrounding. This includes static objects such as road edges, road markings. It has to understand very complex structures of the lanes. Um, and I'm not talking now about bringing information from HD maps, but only about the onboard scene understanding, which comes from perception, signs, and then there are all kinds of obstacles such as clutter, construction zone cones, and so on. But also we need to detect dynamic obstacles. Now this includes classified objects such as cars, pedestrians, bicycles, animals, and so on, but also general obstacles like the cart in the example here, which is very difficult to classify to a known class of objects on the road. And it can include all other types of general obstacles which we do not have a specific classifier for. Um, so all these tasks we are commonly approached by sensor fusion, and the predominant approach is to use machine learning in order to learn how to detect this from training data. Um, just 1 second. Ayrton, I seem to have a technical problem.
Oh, okay.
Okay, it seems to be solved. Okay, I was asked for
Okay,
some
perfect.
password. It's probably something with the proxy here at work.
Ah, okay. Yeah, just let me know if something is going wrong. But now
Uh,
everything's fine, yeah?
it looks okay so far.
Okay. Okay, perfect.
Okay, so as I said, this is commonly approached by machine learning. So this is an example of a work that we did here, which I'll discuss also later, in which there is a deep neural network which receives visual data from cameras, and it is able to detect both the static obstacles, the dynamic obstacles, and the unclassified obstacles by combining two different technologies. One is the standard object detection, which is symbolized here by the bounding boxes, with the color being the class of the object. And the other is a general obstacle detection marked by the blue rectangles, the field ones, which is supposed to detect any type of obstacle. And as you can see in these examples, there are all kinds of obstacles which are not detected by the regular detector because we did not learn their class, and therefore it's important to combine both technologies in onboard sensing. Um, just to deep dive a little bit more into the obstacle detection issue, so there are several tasks which have different names in the literature. One is road segmentation. It's usually accomplished by vision using a mono camera and an approach called semantic segmentation, in which the drivable surface is detected. The other is general obstacle detection. So the road segmentation is marked here in the green as a pixel segmentation. The general obstacle detection is marked in blue, which it's supposed to detect all the obstacles above a certain height, and all the flat and non-flat delimiters, and it's usually solved by 3D sensors such as stereo or Lidar, and you can see the difference between these two, and I will touch upon it later on. Um, okay, so we are all aware of the importance of training data for training machine learning models, and specifically for deep networks. This is a known results from 2017 on the effectiveness of data, showing that if you have a weakly labeled data, but with millions and millions of example, and you use it as a starting point, and then do fine tuning from it, then you can improve object detection just by using more and more and more data. So unfortunately, this is the still the situation in deep learning, which is very data hungry, and we need to supply it with lots and lots of data. So how do we go about and get this data? This is one of the major problems of machine learning, and solving it is a key for any real production implementation. Um, the most prominent approach used by many companies today is simply manual annotation. This is an example from the cityscapes dataset, in which each pixel is marked with a class. This was obtained by people that annotated the boundaries of each of the objects, and this takes about 60 minutes per image to do very accurately. So you can understand why big companies in this area hire sometimes thousands of annotators just to work on annotating the data that they collect. So of course the drawback is this is um, very expensive and requires a lot of labor. Um, Another approach is to use computer graphics simulated data. This is an example. So if we have simulated data, then we have the full ground truth of where are all the obstacles and what is their class, and this is very nice. However, there are still issues with photorealism and transferring a network that was trained on such data to real data. This is a big research topic today. And still, we do not escape from the labor issue because we need to generate scenarios. And scenario generation, especially if you want to reach a very photorealistic or world realistic simulation, that is also a very difficult problem. There are several examples of successful usage of simulated data. For example, the FlowNet, which was trained using the flying chairs dataset, which is basically a very non-realistic dataset. But for this specific low-level task of optical flow, it was very efficient in training a network that was then able to work on real-world images. And the approach that I'm going to talk in this lecture is to use automated ground truth or cross-sensor learning. So you can see here an example of a network trained to detect free space in a way that is very similar to what we can obtain from LiDARs. And indeed, this network uses only camera in order to detect the free space, but in the training phase, it used the Velodyne LiDAR in order to automatically annotate the examples. So you see here a result of a network in which there was no human labeling in the process of its training. Everything was done automatically. An example of such automated training is using stereo to train monocular camera to detect depth from a single image. And this is also something that is a hot research topic. And there are, since this work that I'm showing here, there are many other works that are improving upon this and showing promising results in obtaining depth from a single image. And again, there is no manual labeling in this approach. You just use the stereo as the supervisor. And this is another example from 2016 on detecting the road area using supervision from maps. So all these are examples of automated ground truth. I'll try to scope it in a more general way. So in the most general setting, we have a vehicle that is driving, and on this vehicle there are multiple sensors, and we can divide them into two sets, which are not necessarily mutually exclusive. We have the target sensors, which are the sensors that will be used in production for the detection, the perception, and there are the supervising sensors, which are used only offline in order to generate training data. And the first prerequisite is to have full alignment and synchronization between the sensors. I will also say that the more co-located the sensors are, the better the results of this entire process will be, because there will be less areas in the world that are seen by one sensor and not by the other. And I'll show using one example. Let's say that the task that we have is object detection. And so the classical object detection, the target sensor is therefore a camera, let's say a forward camera. It's supposed to detect pedestrians, cars, and bicycles. And we can and we define the supervising sensors as both the camera and the Velodyne LiDAR mounted on the vehicle. We then collect a dataset of using both sensors, the supervising and the target sensor, in a synchronized way, and then we develop algorithms which are the automated ground truth algorithm that computes the task on the supervising sensors. In this case, the task is object detection. So it needs to take the camera input and the LiDAR input and perform object detection. We need to note that there are two main things that make this task easier than the actual perception task. The first is that we can do it offline. So the running time is of less importance than for onboard perception. We can have much more powerful computation platforms, and we can wait more time until we have all the data annotated. The second thing is temporal causation. So we do not need to look at a single frame. We can look at multiple frames. We can go to the past. We can go to the future. And these are things that we cannot do in onboard perception. So it makes the task a little easier. And of course, we can have more powerful sensors, as in the case of the Velodyne. The second stage is to project all the ground truth that was generated to the sensor domain. And this
is that actually indicating whether
I'm sorry, I didn't hear you very well. Can you repeat the question?
Was there a question from the audience? Maybe there was another
Maybe.
speaker who was part of the organizer
Okay.
panel. In that
Okay.
case, feel free to send me the questions so we can go through these after the session. But I mean, for the moment, I think he was just logging in and had this volume on. So feel free to go on then.
Okay, no problem. Okay. So as I said, the second stage is to project the output that we got in the automated ground truth to the target sensor domain. In this case, draw these rectangles very nicely on the image. And then we just get data with ground truth. And we can use the ground truth together with the yellow part of the data, which is the target sensor, in order to train our network end to end. And as you can see, all this process did not require any manual label. Okay, so what are the pros and cons of this approach? So first time we solve an easier problem. As we saw, there is no temporal causation issues, and we have less issues with running time. Another important thing to understand is that we do not necessarily need completeness. So you can imagine that we only annotate the easy parts of the image or some parts, and then if we are able, we can ignore the rest of the parts of the image or areas in which we are not very sure of. So in contrast to perception, we do not need to be complete for our data set. And the promise is, of course, to have scalability, so you can just collect as much data as you want, and you get the annotation for free. And theoretically, you can get continuous unbounded improvement of your network. The difficulties are that first it's a challenging setup to have all the sensors together synchronized and seeing the same area of the scene. And of course, the annotation quality and accuracy are not guaranteed, as they are many times for good manual labeling. The third issue is something that I will claim that is not as severe as it seems. So there are, if I'll be the devil's advocate for a second, I can say, wait a minute. If you are detecting objects with a LiDAR, then you are limited to what the LiDAR can do. If the LiDAR has 40 meters range, then you will not be able to train your model to detect objects beyond 40 meters. But actually, this is sometimes we can bypass this. So I will show examples in which we can learn beyond the supervising sensor capabilities. And also, we can even learn from the same sensor, but achieve better results than we could before. So this is a type of bootstrapping. Okay, so I'll start with the example for general obstacle detection. This is the first work that we did in this area. We had the Velodyne Lidar as a supervising sensor. We had the front camera as a target sensor. And the task was to detect general obstacles, which is defined as detecting in each column in the image, the position of the nearest obstacle above a certain height, 20 centimeters, height that is higher than the height of a curb, in that column in the image. This is a work published in 2015. So you can think of the input as being a stripe in the image and the output as the Y location of the nearest obstacle in that stripe. We call this network the Stixel net. In our first version of it, we used the Kitty dataset in order to train our network. So we have a Velodyne, which is synchronized and calibrated. And we used the raw images, which was 56 sequences. And it's not part of the benchmark of the Kitty dataset. So we created our own benchmark, which is publicly available. So anyone can try to improve our results on this benchmark. It basically contains 6,000 images and 800 test images. And from this data, we automatically get over 300,000 training columns in each image and about 60,000 for testing. So how do we do it? We actually started with a very, very simple algorithm in which we project the LiDAR points onto the image plane. We interpolate depth to all pixels, and then we find columns with a profile typical to transition from road to roughly vertical obstacle. It's a very simplistic heuristic algorithm, and it's generated this type of ground truth. So if you see there are part of the columns marked by these white circles, but they are far from being complete. So for columns that we were not sure, we just threw them away. And it had several limitations. It could not detect very close obstacles because we project everything to the image. So if the contact point of the obstacle and the road is not in the image boundaries, then we discarded this column. And also it could not detect clear columns in which there was an obstacle farther away from the Velodyne distance. And in general, it had a low coverage of about 30% of the columns. And when we did the training, all the other columns went into ignore. And we trained a very thin, only a small CNN with 5 layers, and it produced an output which was semi-discrete. So we divided the Y positions into bins, and we had ability to interpolate between bins. And in general, this is the type of result we obtained with this approach. So you can see that just from using automated ground truth, we could reach some nice monocular camera-based general obstacle detection, but you can see that it's very noisy and it does many mistakes that the LiDAR would not do. So Ayrton, do you see the video running at some reasonable pace?
Yes, it's working fine. It's quite fluent, so no worries.
Okay, great. So, and these are experimental results which showed for each of the errors. Let's say that we look at one column and we ask, is the error how much is the error in pixels? Is it 5 pixels, 10 pixels? And then we ask how many columns have error with less than 10 pixels. This is the x-axis. And the y-axis gives the fraction of the results within that range. So you can see that the StixelNet reached an average of this curve of 0.87, and for, let's say, for 10 pixels error, almost 85% of the examples were within this error. And we also we showed that previous non-deep results were not even close to solving the problem. So this is actually a problem that was not solvable before deep learning. And we even compared to a stereo algorithm that ran on the same data and showed comparison results to stereo. So this is these are a few examples showing the comparison to stereo. So what you can see in red, the stereo, we implemented the Badino's method from 2009. There are issues with the columns that are the obstacle is relatively distant, and the monocular approach does not have this limitation. So in some aspects, it is even better than using stereo. Okay, a second application that we tried is to do obstacle classification. So now that we have detected the obstacles, we want to know not only that there is an obstacle, but also what is its class. So in this case, we used both the camera and the Lidar as the supervising sensor. And I thought there was an example attached to it. So you can see in red the pedestrians in the example, and this is actually interesting because we used classical object detection in the camera, but also cues from the LiDAR in order to eliminate false alarms and misses. Okay, another example. Sorry. Okay, so here is the example, the movie example of a network, again, trained fully automatically, which is able to detect general obstacles and also classify them as being a pedestrian or not being a pedestrian. So in order to generate the automated ground truth, we use the classical obstacle detector, and then for each bounding box detected, we use some characteristics from the LiDAR data in order to improve the detection of pedestrians. Okay. And then we went back to revisit our general obstacle detection, and we thought that our automated ground truth is very simplistic. So these are results from a paper we published in ICCV about a year and a half ago for the unified network for obstacle detection and object detection. And what we did basically is we improved the algorithm for obstacle detection and made it object-centric. So we first estimate and subtract the road plane, and then we do 3D clustering in the LiDAR domain of objects. So before projecting them to the image, we do some processing of the LiDAR. And then we get objects with clusters. We can then project them to the image, smooth the bottom part of each object using dynamic programming. And now we can also handle clear columns in which there was no object above 5 centimeters and there were far enough returns from the LiDAR. And also near obstacles. So if we detect an object, we can estimate where it hits the ground. We can just classify it as a very near obstacle. So we have a much larger coverage. You can see examples of the old versus new automated ground truth. The new automated ground truth is in red, and it can capture many more examples that the old one couldn't. And in terms of performance, and also we collected our own internal data set. So you can see in the left image the way that we mounted the Velodyne LiDAR in the same location as a camera. This camera is actually a fisheye lens camera, and it is mounted in a similar position to production cameras for surround vision in vehicles. And it's a very different setup than the Kitty dataset. And we collected a large amount of examples, and then trained a neural network which has an object detection branch, but also a bit larger STIXelnet 2 architecture, which detects the general obstacles. And you can see that just by using this external dataset and the new automated ground truth, we were able to reach much more reliable obstacle detection on the Kitty dataset. And this is interesting because many of our examples were from fisheye lens cameras. So it was nice to see that you can mix and match datasets with very different camera characteristics into one dataset. And I'll show some quantitative results for this. So this just shows that the performance using the new automated ground truth is better even when you exclude the cases that the old AGT could not handle. But what's even more interesting is the cross dataset generalization. So you can see that training on both datasets, our internal one and Kitty, is better or as good as training on each one of the datasets for both tasks. So now we have a combined dataset that can make use of more data, even if it comes from different sources. Any questions so far?
Well, I think at the moment everybody is satisfied.
Okay.
So you're leaving no questions open, but yeah.
I'll continue. Okay.
Okay.
So the next task I'll show, which I'm starting to touch now about exceeding limitations of the teaching sensor. So the task is to do pose estimation of vehicles, and the supervising sensors are Lidars, IMU camera, and the target sensor is a camera. And what we do is I'll show how we are able to generalize from dynamic cars to static cars. So one of the problem of if you just use LiDAR to detect car pose, then it is usually very difficult to detect a car that is coming towards you from a car that is driving away from you in cases in which the car is static. If the car is dynamic, then there is no problem. You can track it and you can understand where its front is at. But if the car is static, for example, in intersections, it's very difficult to determine the pose. Using vision, it's easier to determine the pose, but we do not have training data to do so. So what we do is we train with the LiDAR data using only dynamic vehicles. And then using the tracking, we can assign for each frame and each car its pose, and we parameterize it using 8 orientation bins. And then you can see the arrows showing the pose of the vehicle as detected by camera only from a network which was trained with automated ground truth. In this case, it was also mixed with some manual annotation. But I think the main point is that before we had a teacher that was not able to detect the direction of static cars, and now we have a student which is able to detect static cars because the camera doesn't care that it was trained on dynamic cars. From a single frame point of view, this is the same appearance. Another such example is the ability to detect to do obstacle detection at far range. So if you look at the small white triangles, you can see that what we have here is a StixelNet, which operates on ranges up to 120 meters. And it was trained using a LiDAR that can detect obstacles only at a distance which is about 40 meters. So how do we do it? We simply train it on the full images, and then when we apply the network, we cut the center part of the image and apply the StixelNet to the center part. From an appearance point of view, the camera cannot distinguish between a far range, which is enlarged, and the near range. So again, we have a camera which is able to detect farther away than the supervising sensor did. And a last example, another example is automated ground truth for curb detection. Now this is a problem which is, it's rather difficult even for LiDAR. We do aggregation of LiDAR, and then we look using some specially designed filters to detect curves, but we have a very non-complete data set. However, the train network is able, and this is the greenish lines, it's able to extend it to the full extent of the curve. And finally, we did free space, which is similar to road segmentation. And for this, we developed an entirely new automated ground truth, which analyzes each beam of the LiDAR and tries to characterize when the beam of the LiDAR leaves the free space and touches an obstacle. 1 second. Again, some technical difficulties. Okay. And I'll show you now some results. And the free space, as opposed to general obstacles, is, first of all, it's supposed to detect the curbs. So anything that limits the free space, even if it's very small, needs to be detected. And also, you can see in the upper image that it detects the projection of the obstacle to the free space and not the image delineation of the object. And this is important if you want to estimate distance to the end of the free space. And I'll show some movies. Again, this is a network which is fully trained automatically. It's able to detect objects, their 3D pose, but it's also, it detects the free space, that's the greenish areas. In this case, this is using production fisheye lens camera, and the image is projected to a cylindrical. It's using a cylindrical projection, so all the obstacles look upright. But this is a fisheye lens camera mounted in very low on the vehicle. Here are some more examples. So you can see that the free space there was a woman that just went past the camera and it wasn't detected by the bounding box detector, but the free space complements the bounding box detection technology and is able to detect even obstacles which are at zero distance from the car. This is a current problem for pedestrian detection using surround viewing systems, the very near obstacles. This is another example. You can see some roundabouts. Now, if I pause it for a second, you can see that there are areas, because we are looking at the column-based approach, areas that the free space cannot cover. So even though we did that, we were able to fine-tune it for the road segmentation, KITI segmentation benchmark, and reach state-of-the-art accuracy on this public benchmark, and our results on this are public, using just automated annotation. Okay, some of the challenges is how accurate is the ground truth. So this really depends on the algorithm. You can see that sometimes there are misalignments which are causing either from calibration or synchronization issues, which cause the automated ground truth not to be aligned with the image. Sometimes we use some assumptions like a flat road, which makes the ground truth not very accurate. Sometimes there is assumption that the road starts at the bottom, so here it is very difficult for the ground truth to distinguish between a bicycle lane and the road, which one is part of the free space, which one is not. So there are still many challenges to using automated tools for ground truth, but I think that the paradigm that will be successful in the future is to use all types of annotation, both manual, automated annotation, and simulated data, and use each one to improve the other. So the manual annotation can be used to bootstrap automatic ground truth, and simulated data, I think, is more useful for generating specific scenarios to test autonomous driving in these scenarios. That's it. Thank you very much.
Thank you very much for your presentation. We now have time for some questions. I will just read them out for you, Dan, and maybe you can comment. The first one is, does ScaleUp also do pedestrian, non-pedestrian classification or only object detection? Dan?
The ScaleUp 2, as it is at the moment, does only general obstacle detection. I think that we decided that the bounding box for classification is a much more reliable and efficient way to classify the obstacles. And therefore, the concept that we chose was the unified network, which does both the bounding box object detection and the general obstacle detection, but we do not classify each general obstacle, but instead rely on the bounding boxes.
Okay, thank you. The second one, is there any use of a high definition map to support the detection, knowing the lane position exactly?
No comment. So, of course, this is possible.
Okay. And well, then I'll just move on. The next question is, what kind of data recording hardware and software was used in the GM vehicle, and what solution for multi-sensor streams time synchronization is used?
Okay, so I'm going to have to disappoint the person that asked the question because I can say only about the tools used in this study. This study was done in GM research and was then moved to GM engineering. And in GM engineering, there are very standardized tools which I cannot comment about. But for this study, all the software for synchronization of the data was developed by us. So it's proprietary software. There is not any standard tool that we used in this study.